Okay, I think it's a good time to start. So it's my honor to introduce Professor Liang from Southern University of Science and Technology. So he is an expert in the higher category. And today he's going to talk about higher condensation theory. So please welcome Professor Liang.
Thank you. Can you hear me? Yeah. Okay. Thank you very much for the introduction. So very happy to be in this wonderful conference. So today I'm going to talk about higher condensation theory, which has come from the paper already online. So first, I want to introduce my collaborator, the two students, Zhi-Hao Zhang, who just graduated, will become a postdoc in Binza in the coming months, and Jiaheng Zhao, he's still graduate. Well, he haven't started the PhD program yet. Okay, and Hao Zheng is faculty in Binza. Okay, all right. So one of the fundamental themes in modern theoretical physics is to establish a new paradigm of phase and phase sensation that can be unified traditional spontaneous symmetry breaking phase with exotic new phases discovered after 1980s, including topological orders, symmetry protected and enriched topological orders, and perhaps certain gapless phases. Okay, this yet to be established new paradigm to be a theoretical framework that can catch the universal and model-independent feature of these quantum phases and phase sensation among them. Okay, so it was known that many phase sensation among topological orders are driven by the condensation of a topological defect, such as the 0 plus 1D defect. This is space-time dimension. Okay, so that's just a particle. If you look at the spatial dimension, it's just a particle or anyon, and a higher dimensional topological defect. A process which was viewed recently as the gating of non-invertible symmetries. Okay, therefore, the mathematical theory of defect condensations, which is indeed universal and model independent, is an indispensable ingredient of the new paradigm of phase sensations. Okay, so let me briefly review what the anyon condensation in 2 plus 1D. Okay, it was well known that anomaly-free 2 plus 1D topological order up to invertible ones or chiral central charge can be described by modulations of category. The objects in the category are called anyons. Okay, an anyon condensation from one modulus of category to another. Imagine this picture. You have a phase, and in a certain large region, some condensation happens. It produces a new phase called condensed phase. Okay, and between them there is a gap boundary. Okay, gap boundary M. Well, this condensation is determined by a condensable E2 algebra in C. As a consequence, everything else was determined by this condensable algebra. In particular, D is a category of deconfined particle. Okay, the condensed phase contains all the so-called deconfined particle is mathematically given by the category of local A module in C, and the trivial anyon in D is precisely this A in C. Okay, and the tensor product in the condensed phase is given by the relative tensor product over A. And M consists of the category of consists of a confined particle, and mathematically it can be described by a category of red A module in C. Okay, this is old theory, more than 10 years ago. Let me give you one example. Recall that Ising modulus category has 3 simple objects, 1 per psi sigma, and let's see the double Ising modulus category. That means it contains 9 simple objects. Okay, another I will consider the condensed phase, which is given by so-called power code modulus category. Mathematically, it can be described by the dream field center of the rect Z2. Okay. And you consider a condenser algebra in this double Ising modulus category given by the direct sum of 1, 1 and the psi. Okay, this is quite well known. And by condensing this A, we obtain the power code from double Ising. This is perhaps one of the most important example in the development of anyon condensation theory. Okay. Yes. I don't know. Sorry. Yes. Oh, yeah. Yeah. Could be. Yeah, I don't know. I don't know that example. Why did? Yeah. Why is this example historical? Yeah. Yeah. Double Ising. Yes. Yeah. Okay, so contrary to the physical intuition that the phase transition between two phases are reversible, about mathematical description of anyon condensation is not reversible because we have the following relation between the quantum dimension of the condensed phase and the quantum dimension of the initial phase. Because the quantum dimension of the algebra, condensed algebra, is always bigger than 1 for any non-trivial condensation. So this is always reduced the dimension. The example of that is this one, okay? Original one is 16. The quantum dimension of it is 2. It's reduced. Cannot go backward, okay? All right, this turned out that this phenomena, one-way phenomena, is a reflection of the fact that the category of anyons, which is defect of codimension 2, does not include all the topological defect in the topological order. Okay? In this talk, I will show by including all topological defect of codimension 1 and higher, we obtain a fusion 2 category and a complete defect condensation theory, and which is ready to be generalized in higher dimension. Okay? All right, so before I do that, I need a review of the theory of the category of topological defect for generic topological order. So the mathematical theory of topological defect for arbitrary dimension topological order was developed in serious work based on 3 guiding principles. One of the guiding principles is the remote detector principle. I will talk about it later when I appear. Another is a boundary block relation. Another is so-called condensation completion principle. And this theory was first speculated without knowing how to define the fusion higher category, and was fully established by Johnson Free, okay, 4 years ago, and was further developed later. So let me summarize the main results of this theory for a potentially anomalous n+1d topological order. Okay, so this is a space-time dimension. Okay, this superscript is space-time dimension. So the category of all topological defect, including codimension 1 and higher, form a fusion N category, okay? Sometimes we also call it the E1 fusion N category. And the zero morphism, or simply objects, are 1 codimensional defect, okay? 1 morphism are 2 codimensional defect, K morphism are K+1 codimensional defect, and the highest ones, N morphisms, are N+1 codimensional defect. This N+1 already matched with the space-time dimension, so the real dimension is actually 0D. So 0D defect in space-time is also called instanton sometimes. Okay? And among all the codimension 1 defect, there is a trivial one. Always use this to label it. Okay? And then you can use that to define the so-called looping of C, which is the endomorphism from the trivial object to trivial object. Okay? And because morphism between trivial codimension 1 defect, between the trivial one, is nothing but a defect of codimension 2, right? Codimension 2 defect is defect between 2 trivial codimension 1 defect. All right, so this is loop C, is omega C is nothing but a category of defect of codimension 2 and higher. And it is turned out to be a braided fusion N-1 category, and also called it E2 fusion N-1 category. And you can repeat the procedure by doing omega K-1 times. You get a category of defect for dimension K and higher, and it turned out that this is a EK fusion higher category. Okay, I won't explain the meaning of fusion. You can just take it as a monoidal, as the same thing to physicists, not same thing to mathematicians. So I will ignore that. But I will explain the meaning of the E1, E2, and EK in the next slides. Okay, so C is an E1 fusion because that's because the 2 codimension 1 defect can be fused in 1 transversal direction. Because codimension 1, you have 1 transversal direction. You can fuse along that way. That will give you a tensor product that explains the meaning of E1 fusion. You consider omega C, that's the E2 fusion because any 2 codimension defect can be fused in 2 orthogonal directions. I draw a picture here. This is plane, so this is codimension 2, right? The 4 codimension 2, it can be fused in 2 ways. You can fuse A horizontally with C, okay? And you can also fuse B with A vertically, okay? This 2 tensor product structure actually is equivalent to the braiding structure, okay? That's important. You can do the braiding. Similarly, if you do a K-1 looping of C, you get a EK fusion. That means any 2 K codimensional defect, okay, can be fused in K independent directions. Okay, that's the intuition of that. All right, let me give you one example, okay? So this is the famous topological topological order in 3D, 2 plus 1D. We denote the fusion 2 category of the topological defect by TC because this is a famous so-called power code, so I will just denote the TC. In this category, if you look once, right? If you loop TC, that means you got the codimension 2. Codimension 2 in this case is nothing but 0 plus 1D defect. 0 plus 1D just particle, so they're anyons, okay? There are 4 simple anyons, 1 EMF, they have famous fusion rules. Mathematically, this can be identified with the dream field center of the Rev 2, okay? And the fusion 2 category, TC, consists of 6 simple objects. Remember, the objects are 1 codimensional topological defects, okay? There are 6 of them, okay? The label might be, so this zeta is an invertible one, this is a trivial one, and what is SS? Remember, power code have 2 type of gap boundary, okay? One is smooth boundary, and another is the rough boundary. You use the smooth boundary, okay? You use 2 smooth boundary to cut power code. That become, you view it from far away, this SS is nothing but the codimension 1 defect inside power code, okay? Similarly, you can do the same thing for the rough boundary. That's RR, that's RS. This is SR simply means just combination of 2 boundaries. Use a codimension 1 defect, so on and so forth. Okay, there are 6 of them, and this is the fusion rule. Okay. All right, let me give you another example. I think topological orders in 3D. We denote the fusion 2 category of topological defect as IS. Okay, for obvious reason. In this case, 1 category. But if you loop IS, that consists of all the codimension 2 defect, right? In this case, it's anyon. Are well-known IC modulation category. It consists of 3 simple objects with the famous fusion rules. It turned out that IS3 has no non-trivial 1D topological order. I simply follow from mathematical fact by Fuchs, Runkel, Schreiber a long time ago. Professor Fuchs also sitting in the audience. Okay, so as a consequence of this, IS is just 1 point delooping of that. Okay, because except the trivial topological codimension 1 topological defect, there is no other. Okay. All right. So next is quite important is that we denote the category of defect of a trivial topological order by NVAC, okay, which consists of only trivial k-dimensional defect. Okay. What is the trivial k-dimensional defect? That's just the trivial topological order of k dimension. Okay. Yeah. So in the trivial phase, what is the k-dimensional defect? That's just a k-dimensional topological order, anomaly free topological order. Okay, but for the trivial defect, that's have to be the trivial topological order. Okay, denoted as 1k. Okay, and there are condensation descendant. What is the meaning of condensation descendant? Defect that can be obtained from this trivial defect via condensation. Okay, that's called condensation descendant. So, for example, you start from 0 VAC. That's just a 0 category, which is a complex number. If you want to do quantum mechanics, you need to add a C-linear structure. And the trivial defect, the trivial topological order in 2D, that's given by, so the category of defect is given by 1 VAC. That's just a category of vector space. You can view it as delooping of C. What is delooping of C? It consists of 2 processes. One is you do a 1 point delooping, okay? You do a 1 point delooping, and C becomes the morphism in this category, in this 1 category, okay? I will ignore other object you need to add into this 1 VAC because you need to add all the direct sums. I will ignore that. I will just draw the simple one, okay? So this delooping consists of 2 processes. First, you do a 1 point delooping, then you add car. What does the meaning of car? Car just means adding all the condensation descendants. But in this case, there's no condensation descendant. Okay, so in this case, car is trivial. And the similarity you do for the 2 plus 1D. In this case, you get a 2 VAC. Again, it's a delooping of VAC. This notation means delooping, and you first do 1 point delooping, then you do car. Okay, and do a condensation. Car is Karoubi completion. It's also called a condensation completion. Okay, so you deloop it, right? You deloop it as Euro, but in this case, when you do car, you didn't add anything. This simply comes from the fact that there is no non-trivial 1 plus 1D topological order. Okay, anomaly-free topological order. But if you move on for the higher dimension, then the things become much more complicated. Again, you do the same thing. You do it iteratively. Assume that n-1 defect was vac was defined, then do the looping. Okay, and it will produce n vac. But in this case, it's contain more objects. You can do the delooping, right? That's the trivial topological order. And n-1 defect is endomorphisms. But now in this case, you need to add more object, because from the trivial topological order, they are connected to certain topological order, which is called non-chiral topological order, which means it emits a gap boundary. Once it had emit a gap boundary, we will show in my talk that you can obtain B by condensing something in the trivial phase. Okay, and this domain wall. So the one morphism is simply given by a gap boundary of B, and is an object in a certain category. Okay, so the M is really this curly M usually means a category of boundary conditions. Okay, so they label boundary conditions. So in general, morphism can be denoted as a pair. Okay, know that in the n-vac, it's connected in the sense that any two simple objects are connected by non-zero one morphism. All right. Why? Because every one of them is descendant of one, so every one of them is connected to one. Okay. Yeah. Because they're all condensation descendant of one, so they're connected. All right. Okay. So next is a theorem which says that once you define the n plus one vac, you can use the uniter functor. Okay, it turns out that this uniter functor is fully faithful, and we call an object in the image of this functor a separable n category. As a consequence, the category n plus one vac is precisely the category of a separable n category. Okay, so this category, this functor is convenient is because at the very beginning, if you look at this category, this B is just a label. But Hom space have physical meaning. Remember, the Hom space catch all the topological defects, and this B is only a notation for, it's only a label for the topological order. Okay, but by using this uniter functor, you provide some physical meaning to the object, because in this case, let's set A equal to n-1 vac. Okay, and this equivalence of the two categories, now this data become this data. Okay, not only they have a mathematical meaning, they also have physical meaning, because remember, this is a category of boundary conditions. Okay, and now this M become this M, so this object become a boundary condition, category of boundary condition. It will turn out to be useful in my later slides. Okay, once we define what the meaning of a separable n category, you can use this concept to define a much more advanced concept called the EM multifusion n category. Okay, it is a condensation complete or Karoubi complete C-linear EM monoidal n category, such that by delooping m times, okay, in order to be able to delooping m times, you need to have a certain structure. That certain structure is called EM monoidal. But you can ignore it, just assuming that, oh, this can be done. This iterated delooping can be done. Okay, after you do that, you obtain a separable n category. So once we have a definition of separable n category, you are able to define a much more advanced notion. This strategy turned out to be very convenient. By the way, when tensor unit is simple, this A is called the EM fusion. Okay, remember that we have encountered this term before. What is EM fusion? Just means that you have fusion product in m independent directions, roughly speaking. Okay. All right. I hope I won't go too fast. So any questions if you want to stop me, okay? All right. So similarly, once you have a multifusion n category, you can compute this delooping, which is the one-point delooping followed by the Karoubi completion or condensation completion by this uniter functor. Basically, what is the delooping of A is nothing but computing right A modules in all the separable n categories. So that's all the separable A modules, basically. Okay. All right. With all this, as my preparation, I can summarize the category, the theory of a category defect. So so the category of defect in a n plus 1D topological order is an E1 fusion N category, and the category of iterated omega k minus 1 C is a defect of codimension k, and higher, and is EP fusion. We already said that. It's just summary. And another one is that the gravitational anomaly of a topological order is characterized by a one-dimensional higher topological order, okay, denoted as the bulk of C. So B is the bulk of C, such that the codimension, the category of a codimension 2 defect in B is given by the Drinfeld center of C. C is the category of topological defect in C. All defect, okay? If C is anomaly-free just means the bulk is trivial. Okay, it does not have a gravitational anomaly. In this case, C is a non-degenerate fusion N category. In particular, it means the Drinfeld center have to be trivial. Recall that the Drinfeld center equal to the topological defect of dimension 2 in the bulk, but the bulk is trivial, so this have to be true. And equivalently, the omega C is a non-degenerate British fusion 1 category. Non-degenerate means that the Newberg center of that is also trivial, okay? Because another interesting result is this. Because so-called the braiding detect principle, which says that all the defects can be detected from each other by using double braidings. However, codimension 1 defect cannot be braided. Only codimension 2 defect can be braided. As a consequence of this fact, all the codimension 1 defect have to be condensation descendant of codimension 2 defect if the topological order is non-free. Okay. If this condition does not satisfy, this simply means that you need additional bulk, one-dimensional higher thing to detect it. Okay. But if you assume this anomaly-free, this has to be true. Okay. This provides an interesting coordinate to understand the fusion in category C. All right, this is a summary of the result we needed. Now we enter the main theme of this talk. Where am I? Okay, good. Okay. Condensation of one-dimensional defect. Okay. So before I start, let me introduce a terminology which will be convenient. Two topological order are all Morita equivalent if they share the same block and connected by a gap domain wall as depicted from this picture. Okay. And in this section, we show how to condense a one codimensional defect in C to obtain D as a condensed space. Okay. I want to give a remark is that the theory of one condensation of codimension defect is not entirely new. Okay. It is essentially covered by Galto and Johnson-Fried in a paper 5 years ago, and it was also briefly mentioned in Lantian's paper and in his talk yesterday. Okay, a detailed explanation of this physical condensation process and a systematic construction of example are not yet available. They will be the focus of my talk. Okay, and the condensation theory for higher codimensional defect are developed in my paper, but the paper contains too much thing. We don't have enough time to cover this, but I will, at the end of my talk, I will briefly touch upon it, okay? And the mathematical theory of a condensable or separable EK algebra, the mathematical theory will be developed in the upcoming paper, not covered in this talk. Okay, let's consider a condensation, okay? Let's consider the condensation from C to D. Previously, when I set it up, you have a gravitational anomaly or higher dimensional bulk. For now, I just don't want to draw it just for simplicity. I just consider it on the boundary. Okay, I will depict it in a one space dimension. Okay, of course there are n dimensions, right? All the other dimensions are hiding, not shown in this picture, just for convenience. Okay, now, so what is the condensation procedure that was understood by physicists? Physicists all know how to do this. First thing you do is proliferating this D phase inside the C phase, okay? Just as I show here. You have a C phase, then you cut a lot of segment and fill in this D phase. Of course, with proper boundaries, okay? You do that, okay? Then you shrink the red dashed box. So this red box, okay? You look at the red, you shrink it. What do you mean by shrink? By shrinking it, you view the inside the D phase. what it becomes? It becomes a codimension 1 defect in D phase, right? You shrink the red box. All right, that's the first step. Then that's a shrinking second step. The third step is you annihilate this codimension 1 defect by mapping it to a trivial codimension 1 defect. Then it disappears, right? If you do that, it's become disappeared. Okay, now let's try to understand what this process really means. Okay, I claim this step 2 and 3 define the algebra structure on this A. A is this part. A is this part. Why? Okay, what happened to this A? Look at this A part. If you shrink this A part, or you view it from far away, it becomes a codimension 1 defect in C, right? So A is really a codimension 1 defect in C. This is A, this is another A. Now, if you shrink this red box and annihilate it, simply it gives a map from A tensor A to, because this thing is gone, then the whole region here become another A. So this really defines the morphism from A to A. And you can see this process does not really depends on whether you shrink this red box first or shrink this part second. It doesn't matter. So this tells you that this is algebra structure is associated. Okay, I will ignore the unito. You can try that as an exercise thing. So as a consequence, so this defines the algebra structure on A. If you draw a higher dimensional picture, you can see more clearly. Maybe I'll draw another dimension. So this marcation is that you start from this A, and you move in the space dimension, okay? And at some point, they merge into one. This defines the algebra structure. And the unitary structure, you can also define it, okay? And it also have a co-unit structure and a co-product structure, okay? Now you can even compose them, right? You think about composing them. There is a bubble inside it, right? And this bubble, remember, every morphism in the category of topological defect are itself defects. Every morphism, including this one. So if you compose the co-marcation with the marcation inside there, you create a bubble. And now you can get rid of the bubble by condensing it to the trivial morphism. Remember, trivial morphism is also a trivial defect. Okay, you can talk about how to condense them. I will ignore the details. Basically, of course, the assumption is that the reason you can do that is because this two defects, they're two morphisms, right? But they're two defects as well. They're Morita equivalent as topological defect. This is the requirement. Okay, I won't go through the detail how to define it. It's a subtle issue. Will appear in a more upcoming paper, mathematical theory on the condensable algebras in higher category. And sometimes I will use this notation to represent A is a condensable EK algebra. This is just a notation for this statement. Okay, A is a condensable E1 algebra. I will denote as that. C represents condensable or separable, if you like. All right, so we already figured out A is a algebra. Then, okay, you do something similar. Okay, so you consider this picture. Previously, here's A, here's A, here's A. Now I insert a non-trivial particle in D. Okay, when D is trivial, of course, this is just still A, right? So know that A is precisely the trivial trivial defect viewed as object in C. Okay, because D can be viewed as a subcategory of C. Why? Because D is condensed from C. So if D is condensed from C, every object in D or every morphism in D should come from the morphism in C. So this is really a subcategory. So you can, by forgetting, so D is a subcategory of C. Any non-trivial, the trivial codimension 1 defect in D can be viewed as automatically an object in C. Okay, so this become an A in C. That's what we do here. So, but of course, you can also insert a D. I will still, by Bill's terminology, I will still call that D. Okay, for D, it should also be viewed as object in C. Okay, what happened on D? Okay, remember that if D is trivial, this shrinking this red box define a marcation between A and A. Now I replace this one by D. This shrinking red box simply define a left A action on D, right? Okay. So similarly, this shrinking this one will define a right A action on D. As a consequence, so by the procedure 2 and 3, it defined an AA bimodule structure on a particle, shouldn't be a particle, should be a full dimension 1 defect D. Therefore, we conclude that every D-compliant particle in D have to be AA bimodule. Okay, I'll just give a AA bimodule another notation. It has another name called the E1 A modules, because this notation is easy to generalize for higher codimensional defects. Okay, they're identical. Okay. All right, that's our second conclusion. Okay. The third conclusion is that think about the domain wall. M is a separable n category wall conditions. It's not just a single defect there, because defect in D can fuse onto M. Defects in C can also fuse onto M. So M does not consist of single defect. It contains a category of defect. Okay, but in particular, you have to choose one as so-called wall condition. Once you fix the distinguished object in M, it determined already how the defect from C fuse into the boundary, or how the defect in D fuse onto the boundary. So this data is also necessary. Okay. Now, if you look at this data M, assuming M is sitting here, small m is sitting here, and trivial defect in D fuse onto it without changing it, right? So there must be a action on M. If you look at it from the picture, it simply means this one. Okay, M should have A action. Well, if you look at the picture, because the trivial defect in D doesn't do anything, right? That's just trivial. So it's simply, this, in the picture, it simply means this identity. As a consequence, so anything in M, anything in the Curdy M must be right A module. Okay, you can just choose M to be A. Doing the condensation, they naturally choose a choice, but it's just a natural choice. You can choose another one. Okay, and once this is chosen, you also know how the defect in C move onto the boundary M, which is given by this functor. Okay, I would denote as L1, the bulk to wall map, which is from lab, and you also have something similar from right. Okay, so this is defined by this functor. All right, so I basically finished all the physical explanation of the condensation. Let me summarize it. If we choose a condensable algebra A, then the condensed phase and the gap domain are determined by this. Okay, and this is care about that. All right, but now I want to consider a converse statement. What if I don't know the condensable algebra, but I specify the wall condition? Yes, if you do that, you can recover the condensable algebra. More precisely, by shrinking the green line segment. Okay, you have the green line segment. In the C phase, if you shrink it, it turns out that this is simply given you have M here, right? You specify the wall condition, and they give an internal hum in C. This turned out to be a condensable algebra. If you condense this A, you recover the condensed phase and M. Similarly, you can do the similar things. Consider a similar line segment in the D phase. Okay, you shrink it. All right. You got an internal hum. Okay. By condensing this one in D, you recovered C. All right. So this process of one full-dimensional condensation of one full-dimensional defect is completely reversible, which was also mentioned in the Lantian's talk yesterday. I want to give a remark which will be useful in the later slides. How to compute this internal hum. Okay, internal hum can be written as this without any problem, right? Because this tensor unit x on M, this identity. It can be rewritten as a composition of two morphisms, two functors, okay? So this is a tensor product functor. It's nothing but, remember, this is tensor product functor. What is tensor product functor? This is precisely this one, okay? This is precisely this one. So it's L1, okay? Then what, so this one is L1, replace that. And what is this? This turned out to be the right adjoint of L1. So this become a very powerful formula to computing the internal hum. For example, if you already set M to be right A modules, okay, then you run this machine. What did you get? You should recover the A, right? Logically. But yes, you can double check. Okay, that become this, composed with that. Okay, this axon identity C is just A. Okay, but this right adjoint in this case is exactly forgettable functor. So we recover it. Okay. That's a consistent check. Okay, this theory works. All right. So the theory is pretty simple. Now I want to give a non-trivial constructions, the general construction. Let's first consider the case that both the initial phase and the condensed phase are trivial. Even in this case, turn out that the condensation is non-trivial. Okay, a gap domain wall in this case M between these two, because these two are trivial. So the gap domain wall is nothing but an anomaly-free topological order. Again, so this can be described mathematically by a pair. M is the Curdy M. The Curdy M is an indecomposable separable N category of wall conditions, right? Object of wall conditions. So M is a particular wall conditions, okay? And or equivalently is, well, because two sides are anomaly-free, two sides are trivial, so this M is actually anomaly-free topological order of one dimension lower, okay? So in this case, because this is a codimension one, you can work out what is M should be. M, well, because it's indecomposable, you just do a looping of M, then do a delooping, you can recover M. Okay, that's just simply a property of the separable N category. Okay, and because the delooping can also be written as remember that we have a theorem saying that what's the delooping of the multi-fusion N category? Well, it just compute. You can identify it with the right omega M, right module over omega M, okay? In fact, that means a separable right modules, okay? And in this coordinate, this M simply can be identified as omega M in this category, okay? It's the distinguished, very canonical object. Okay? With this in mind, with this coordinate in mind, you can write down this this map. Okay, the left from left side, how this function describes how the bulk excitation or bulk topological defect move onto the domain wall. This function is given by that. Okay, and in particular in this case, it's simply by tensor product omega M. Okay. All right. Because of that, you can compute the right adjoint. The right adjoint turned out to be a forgettable functor. Okay, now you can compute what's the associated condensable algebra is given by this, or composed of two functors. Okay, in this case, L1, you just put in L1 in there. Sorry, 1C, tensor unit of C, that's just omega M. Okay, but this is a forgettable functor, right? Forgettable functor simply give you forget, doing nothing. It's still omega M. So omega M, remember that omega M is what? M is a separable. You do an omega, that become a multi-fusion. Okay, so well, if I assume anomaly free, this actually a fusion N category is precisely the fusion N category is precisely the condensable E1 algebra in that. Okay, that define the condensation. So you define the condensation, you can recover this. Okay, you define the condensation. Let's just plug in our formula. You plug in. So what's the condensed phase? The condensed phase must be the E2 module over this condensable algebra, right? Just do that. But in this case, look, in this case, what do you got? The condensed phase is trivial. Okay, the condensed phase is trivial. So we obtain an interesting formula. Now you apply the same formula for M. Remember, all this formula is fixed. So you don't have any choices. Okay, you see this. You don't have once you have a condensable algebra fixed. All these are fixed. You don't have any choice. Okay. Now you look at what M is. Well, this is just tautological because that by definition M equal to that. Okay. So you can view that the second equivalence as a tautological check. Okay, can be viewed as a consistent check. But the first monodic equivalence is not trivial mathematically. We formulate this result mathematically, which says that given a non-degenerate multi-fusion N category A, why is non-degenerate? Because in M is anomaly free. So the associated category of defect are given by a non-degenerate multi-fusion N category. It's automatically Lagrangian. The meaning of Lagrangian is that by condensing it, by considering the E1 module of that, we got a trivial phase. Okay, this result, well, is highly non-trivial. This result was first proved in the N=1 case due to by David Opennikshi, okay, a few years ago. But this is for N. Oops. Okay. Now we consider slightly the generalization of that situation. Previously, we considered the initial phase is trivial, and another phase here is also trivial, but now we replace it by a non-trivial one, okay? And this is called a non-chiral topological order with a gap to boundary, okay? Now M is an indecomposable several n category as before, and omega M is the small m is particular wall condition, and omega M is the category on the category of defect on the wall, particular wall condition, okay? Is an indecomposable multifusion n-1 category. And the picture is exactly the same as before, except that the D, I changed the 1 to D. Everything else is the same. Everything else is the same. So you run the same logic, you can compute the condensable algebra associated with A. You see, they're the same. They're the same, okay? Except in this case, this omega M is not degenerate anymore. It's degenerate in some sense, okay? So you can compute, you plug into the formula, you compute the E1 module, that will give you the condensed phase. But in this case, right, E1 module is just bimodule, right? You compute it carefully. Bimodule, in this case, is given by a functor from M to M, okay, which is a E0 center of that, okay? That's compatible with the so-called bounded property relations. That's the D, okay, because the boundary property relation says that the topological defect in the block should equal to the center of the topological defect on the boundary. So that's one of the reflection of that fact, okay? So now you can recover D. What's the consequence of this? This consequence is that by condensing omega M as a condensable algebra in NLAG, you can recover all non-chiral topological orders from the trivial phase. Okay, all such topology can be obtained from the trivial phase. We made that statement at in my early slides. Okay, okay, so that's a non-trivial example. Now I'll give you a slightly more non-trivial example. When C is anomaly free, in this case, of course, this C, the curly C, represents the category of topological defect is non-degenerate. What's the meaning of non-degenerate? It means that its dream flow center must be trivial. It does not have a gravitation anomaly. So everything in the higher dimensional box must be trivial. So its dream flow center is trivial. So in this case, remember that it's anomaly free. C can be the delooping of omega C, because all the codimension 1 defects cannot be detected by grading. They have to be condensation descendant. So all the codimension 1 are descendant of codimension 2. So it's a delooping of omega C, sorry. And remember also the sigma can be written as a right module over omega C. That's give a nice coordinate of C. We're going to use that coordinate. We're going to use that coordinate to give a construction. Okay, it provides so this is category series similar to differential geometry. If you want to do a concrete calculation in the differential geometry, you choose a nice chart, right? In a nice coordinate system, you can compute it. Similarly, in a category series, it's the same. In an abstract category, you cannot do any construction or computation. You already provide a nice coordinate. This is a nice coordinate of C. Using this nice coordinate, you can describe a lot of things. For example, now what do you want to know? You want to know, can I classify all the condensation in C, right? Yes, in this case can be classified, and indecomposable condensable E1 algebra in C are precisely or is precisely an indecomposable multifusion n-1 category A equipped with a central functor. What's the meaning of central functor? It simply means that it equipped the braided monoidal functor from omega C to the dream field center of it. Okay? All right, with this powerful theorem, pick any one you like, pick any A you like, you do the condensation, you apply the formula, you got the condensation result. Of course, this, well, it does not shed any light, right? It just, everything looks like this. You just do it bluntly. But now I want to tell you what the physical meaning of this construction. By doing a little bit of computation, of this M, it will reveal the physical meaning of this condensable algebra, right? This condensable algebra looks very mysterious, described in this abstract term. Now I want to compute this M. I'll tell you what the M is. Now you compute this M. M is the right A modules in C, right? But remember, C have a coordinate. So it just replaced by its coordinate. It's a right module over omega C, right? in the previous slides. See, C is put back. All right, you do that. Okay, because a action on anything, that A action already factor through this omega C action. Okay, if you compute this, it turns out that you can ignore this action. Simply compute that. Okay, all right. What we gain from there? Okay, now we can compute the omega m. M is the wall condition, right? By fixing this m, omega m simply tell you what is the topological defect, codimension 1 topological defect living on that wall condition, living on that wall. Okay, it must be a fusion category or multi-fusion category given by that. Okay, you compute it, well, it's just A. Exactly the condensable algebra. So the condensable algebra is nothing, as shown in this picture, this condensable algebra A is nothing but the defect, the fusion, the multi-fusion category of defect leaving on this domain wall, which separated the phase C and the phase D. Okay, that's the physical meaning of that. Well, you wonder, oh, this is A, but wait a minute. If I want to condense this A, I need to view this A as a condensable algebra in C. A condensable algebra in C is in particular a codimension 1 defect in C. Where is that codimension 1 defect? Okay, you can see that from this picture. By bending this picture from right, okay? Now you squeeze this green region. You squeeze the screen region, okay? You got a defect in C. Codimension 1 defect in C. That codimension 1 defect is exactly the defect you're looking for that's associated with A. But you're probably puzzled if you do this naive fusion, that will give the defect leaving on this domain wall, but a codimension 1 defect. But that's not really a label for the codimension defect in the category of C. If you want to know the category, what's the object in the category of C, you should look at this corner. Okay. Previously, I said that the unita functor provide. In general, if you have an abstract category, the object is just a label for something. It does not have physical meaning. But by using unita functor, you can provide physical meaning to the abstract label. In this case, exactly the case. So C, when it's equipped in this coordinate, okay, in this coordinate, it acquired some physical meaning. So the only thing you need to know is that the object is in the object label associated with this topological defect is exactly this corner, omega m, right? But in general, an object in the category might have some algebra structure, but this algebra structure might not have anything to do with the monoidal structure on the omega m in general. But in this case, they're coincide, because look at this picture. This picture tells you that how the modification, what's the algebra structure of omega m. By remember that the category of defect, all the morphisms are defects, okay? So consider this part, this dashed box. The upper dashed box simply represents the omega m relative tensor product over omega c and omega m. That's nothing but A tensor A, okay? But the lower box is again a defect which define a morphism from A tensor A to A. Okay, so how define them? You just fuse them. Well, this is a trivial morphism on M, trivial morphism on M, trivial morphism on M. When you fuse them together, you simply fuse these two dots. This is nothing but the monoidal structure of omega M. So the algebra structure on A is exactly monoidal structure on omega M. This gives a physical meaning. This is actually not only give a physical meaning, it's actually give a physical proof of this mathematical theorem. You can view it as a physical theorem now, okay? Because it tells you that anything you have can viewed as a domain wall between two phases. Start from C, okay? And you got another phase. Anything you put in here, satisfy this condition, satisfy this central functor condition, okay? And by this logic, it automatically define a condensable E1 algebra in C. All right. Then what's the result of condensing it? Okay, the result of condensing it is exactly, the condensed phase is exactly this part. Okay. This to give a physical meaning of this result. Of course, this statement can be said, okay, now instead of computing it, you can have some other way to compute it using centralizer. That's just some inspiration for you. I'm not going to explain it. So it's just telling you, once you know that, you have many other ways to compute it using some fancy mathematics. Okay? But a non-trivial conclusion is that once you have this picture in mind, remember that there was a central functor. Central functor means that there is a braided monoidal functor from omega c to the center of A. When this braided functor is equivalent, what happened? When this equivalent, you can see immediately that you don't need this part. This is already saturated. The center of A is only contain this part. The other part is completely empty. It means that condensable, if you condense this condensable algebra, you get a trivial phase. That's another way to say that this condensable algebra is Lagrangian. Okay? Okay. Let me take a look if I still have time or not. All right, still have 2 minutes. All right, so another example. What if C is not only anomaly free, it has a gapped boundary? In this case, C is a bulk of another topological order itself. Okay, it's a non-chiral. So in this case, turn out that it has a new coordinate system for C. Okay. Well, so C is just a bimodule. Remember what the bimodule? Bimodule is a way to characterize condensed phase. Okay. So this formula already means that if you condense a B off in the N vac, you get C. So C is non-chiral. That's another way to see C is non-chiral. Okay. All right. So and in this case, an indecomposable condensable E1 algebra is precisely an indecomposable multifusion N category M of equipped with a monoidal functor B to A. M of A of just means that you reverse the tensor product in this category. Okay, you have a reverse the tensor product. All right. Once you have a monoidal functor, you will get that. All right. Then you can condensing it, right? Plug into the formula we have, right? Just compute this. But remember that all the A action or automatically defect through the B action. All right. So you can simplify this by getting rid of this by replace it by N vac. So it's very easy. But if you look at this, that's exactly condensing A of in the N vac. N vac is the category of topological defect in the trivial phase. So okay, so in this way you got what do you got? You simply got the bulk of A, which is the topological anomalous topological defect associated with the category, the fusion category A. Okay, and that's just the bulk of that, the center of that, and the moving. So you can compute it very precisely. And the gap domain wall, you can do something similar. Okay, maybe I won't go through the detail here, but in this coordinate, you can also find a lot of easy consequence. For example, if you pick a left B modules, okay, and there is a canonical monoidal functor from B to functor category from X to X, right? That's just ordinary. When B acts on X, it's equivalent to say there is a monoidal functor from B to functor categories X to X, okay? And this automatically defines the Lagrangian E1 algebra. Why? Because you plug into this formula. What is the mod E1 module when you replace A by this one? And we know that this functor category, it's a fusion category. It's a multi-fusion category Morita equivalent to the trivial category. This is Morita equivalent to the N vac. Okay, so you're just basically doing a N vac E1 module of N vac. So you got a trivial phase. So this condense this algebra, you get trivial phase in that sense. This algebra is Lagrangian. Okay. Now, so in this case, we have two coordinates. Remember that in this non-chiral case, non-chiral means already anomaly free. Okay. Automatically means it's anomaly free. So in anomaly free case, we have this coordinate. But in this non-chiral case, we have another coordinate. What's the relation between these two coordinates? So these two definitions are related by following picture. Okay, if you condense A in the first picture, that condensable algebra is exactly the category of defect on the domain wall between the initial phase and the condensed phase. That's in this coordinate, okay? Once you have that, you can easily obtain the same condensation in the second coordinate. How to obtain the same algebra in the second coordinate? You simply fuse, okay? So in this case, you have a op as a boundary of this phase, okay? Okay, because C is equal to that, right? So it has a gap boundary, and the gap boundary exactly given by B or B op, depends on orientation. I have a particular convention for orientation I didn't explain, but this is the A op. Now you fuse them together, okay? You fuse them together, then become A op. So monoidal functor from B op to A op is exactly this sandwich construction. Okay, this become a very popular name for sandwich construction in the theory of SIM-TFT. Yes, this is another sandwich construction, but we have proved a long time ago, nearly 10 years ago, that this sandwich construction defines a morphism between topological order. In particular, it recovers the monoidal functor between fusion categories. So you do the fusion you do this sandwich construction, it automatically gives you a B op to A op. You see how it works. B op is mapped to this B op tensor, this one, and we have a formula to compute this, right? Then you can show that this is A op. All right. So a monoidal functor is exactly the sandwich construction. This tells you the relation between these two. All right. So this general construction of a condensable E1 algebra leads to a classification of a condensation for a finite case theory in 3D and 4D, and many constructions for higher dimensions, which show in our paper, but I don't have time to cover them for today. I will give some examples. Let's see. Okay, we'll have a few minutes. This is just a restatement of the previous result of how to condense from the trivial phase to a non-chiral topological order, but in the 3 dimensions. So I will skip it for the. Okay. So I will give you another example, which is much more well known. A topological defect in a Z2 gauge theory, which is hard-code, right? In this case, you can have because it's normally free, so you have this coordinate, right? You have this coordinate. In this coordinate, we have a complete classification of a condensable E1 algebra, right? It's given by a central functor of that. So let me give you some examples. Consider the identity functor. Well, identity functor is also central. It defines the condensable algebra, which is just the tensor unit of the tensor unit. I mean, trivial topological defect. Okay, in the category of all topological defects. And you also have the forgettable functor, and this defines the condensable E1 algebra, and which is precisely the one codimensional defect SS in TC. Remember that what is the SS? SS is a particular one codimensional defect in the Tauri code model. Okay, and you can see what the result is by condensing that, right? Because inside these two boundaries is empty phase. So D is that empty phase, must be trivial. You can check. Okay, so since the condensed phase is trivial, this SS is actually Lagrangian condensable E1 algebra. Okay, and we know there is another boundary, right? So here comes another way to recover that. So this is also because these two are monoidal equivalents. We map to that is automatically a central functor, which defines the condensable E1 algebra, and the corresponding one full-dimensional defect is precisely RR. Okay, rough boundary and the rough boundary cut the top part code. Okay, again, if you condense it, because in the middle of this two boundary is empty phase, so you must get the empty phase, the trivial phase as the condensed phase. All right. Again, this is a Lagrangian, right? Because the condensed phase is trivial. I'll give you another example. Consider the double icing. Remember, we have this example at the very beginning, right? You have an A defined by 1, psi. By condensing this A from the double icing, you will get particle. But now I want to do the reverse process. Okay, given this A, it turned out that this A is a condensable E2 algebra. Using this A, you can define this the right A modules. Okay, in the double icing. Okay, this K is actually a condensable E1 algebra in Tauri code. And in particular, if you want to see mathematically what the hell is that, it's actually a fusion 1 category. It has explicitly computed, it has 6 simple objects, and all the fusion rules have been computed. If you want to know the detail of this mysterious K, is particularly a fusion 1 category, has been explicitly computed. Now, this K, because it's defined a condensable E1 algebra, by condensing it in Tori code, you obtain the double icing. Remember I said that if you do it in the anyon condensation, you cannot do it reversibly. You can condense double icing to get Tori code, but you cannot get do the anyon condensation of Tori code to get double icing. But by consider codimension 1 defect, you can achieve that. All right, so it's completely reversible. I'll use the remaining few minutes to explain briefly, touch upon the higher dimensional one. So condensing a k codimensional topological defect in a topological order amounts to a k-step process. A k codimensional defect is condensable if it is equipped with a structure of a condensable EK algebra. What is the meaning of EK algebra? It is an algebra equipped with compatible multiplication in k independent directions. Okay, and by condensing A along one of the transversal directions, we obtain a k minus 1 codimensional defect, denoted as a sigma A. Okay, it turned out that this sigma A is naturally equipped with the structure of condensable EK minus 1 algebra. Why? Because this one contains multiplication in many directions. By condensing along the one transversal direction, you only use the one multiplication in one direction. There are k minus 1 remaining. So it become a k condensable EK algebra. So you can further condense it. Okay. In the k step, okay, the last step, condensing a E1 codimension defect, it defines a phase transition to a new phase. Okay, of course, that's just defined by the same formula, right? Defined by the same formula. All right, the k codimensional defect. Well, in this process, how to determine? Well, of course you can. If you want to know k codimensional, define the topological defect. Okay, which is clearly the iterated omega in the D phase, in the condensed phase. It can be computed directly. Okay, of course you can first compute a whole D, then do the looping, right? But it turned out there's a convenient way to do it. You can do it directly because this formula just simply show that simply is a mathematical fact of physical intuitive truth, which says that the k codimensional topological defect is deconfined if it is equipped with a k dimensional A action, which defines a mathematical notion called EK module over A. Okay, and a similar thing you can do for the gap domain wall. When the C is nominally free, in this case, the same phase transition as a k-step process can be alternatively defined by replacing the last two steps by a single step by condensing. Okay, the second to the last algebra or codimension 2 defect in the remaining two transversal directions directly. Okay, this is just similar to anyon condensation. In that case, you compute the E2 modules that will give you the condensed phase. Okay, so when n equal 2, this modified the last step is precisely the Euro anyon condensation. Okay, of course, in n equal 2, it has a new feature. For example, given a normally free 3D topological order, where this, by looping twice, by considering codimension 2 defect, it turned out to be a modular tensor category. By rolling it up, okay, a defect in the spatial dimension, rolling it up in the 3D spatial dimension. Okay, this is 2D spatial. You roll it up as a cylinder, it becomes one-dimensional in 3D. That's codimension 2. It becomes a codimension 2 defect in the trivial bit. Okay, anomaly topological order, roll it up, it becomes a codimension 2 string. You condense this string, you reproduce trivial phase and as condensed phase and the gap domain wall. That means we can even condense topological order. Okay, there have a lot of higher dimensional generalization, which I will skip, but I will tell you one again, the topological Tori code. Okay, this is already known, right? But in this case, remember that anyon condensation theory tell you that okay, we can condense E particle. This is a condensable E2 algebra, okay? But by condensing the E particle, we can do it two different ways. As the anyon condensation, you just condense it directly. But now you can first condense it along the line, produce sigma AE. That's just RR. But we know that we can further condense the string RR, right, to get the trivial phase. That's to produce a rough boundary. Similarly, you can also condense M particles along the line to get the string, then condense the string, give you the trivial phase and the smooth boundary. So that's the connection of this. All right. The last example, maybe I will just say it briefly. For higher category modular higher category with lack of example, the only thing we can think of is the finite gauge theory. In this case, it was conjectured in mathematical literature that what this category of defect looks like. Okay, it looks like something like this. Okay, I won't explain the detail, but just tell you that in this case you have two coordinates, and omega of that is the dream field center of n rep G. You can also compute the iteratively looping. It's just given by the rep G. And when k equal n, you loop n times, you simply recover the category of particles with nothing but the boson, rep G. Okay? In this case, you can consider a subgroup G, and this will produce a commutative algebra in A, which is a function on the quotient of G over H. Okay? This turned out to be a En-1 algebra. You can condense that. Okay, in this rep G, you can condense that. Okay, how are you going to do it? You first condense this algebra along the line. You produce a string. You compute the string, or it can be computed. Okay. Then you further condense the string along another remaining directions. It's sigma 2. It can also be computed. Okay. Until you repeat the process until sigma n-1. In this case, the last step you do is you compute the sigma n. Over the second to the last, you compute this one. But this is a little bit complicated. Okay. But using the coordinate change, because in this case you have a two coordinate, you translate it into another coordinate. It turned out that it just produce another monoidal function from n rep T to n rep H. This is just forgetful function, which can be define a condensable E1 algebra. You condense it, you got the condensed phase. What's the condensed phase in this case? That's exactly just finite gauge theory associated with the group H. Okay, so in this way, we provide precise mathematical theory behind the Fock law of breaking the G gauge symmetry. You got a subgroup, again, H gauge theory. Okay, that's a consistent check. All right, so it tell you that this theory is meaningful, reasonable. Yeah, thank you very much.
So any question from audience?
Yeah.
So very nice talk. So I have a maybe naive question. So from the high energy community, it seems like condensation is just the higher gauging some higher form symmetry.
Yeah.
So normally they have a dual quantum symmetry, which so how to see it from your picture?
Well, they are just because we consider the category of all topological defects. The topological defects are viewed as a non-invertible symmetry or generalized symmetry by energy community, right? It's much more than a higher form symmetry because the higher form symmetry is community. It's many cases invertible, right? But now this condensation theory works for all topological defects, invertible or non-invertible. They all do. For example, in this case, if you want an invertible higher form symmetry, you can consider G to be finite. You can consider G to be finite and abelian.
Okay.
Finite and abelian, then this particle are all invertible. Can be considered a higher form symmetry. But this theory is more general, contain all the non-invertible symmetries. It's a theory for non-invertible symmetry. So G can be non-abelian.
So basically, they just consider all the possible.
Yes, all possible. It's a general theory. It does not. We ask the question not to. If you ask me a particular defect or particular higher form symmetry, can you condense that? I don't know, I have to check, right? But we tell you the requirement. What's the necessary condition for it to be condensed to all the way to the, sometimes if you lack, yeah, that's a good point. So if you have, if this object lacked of some algebra structure, this case step of condensation might stop in the middle. That means this defect can be condensed in some submanifold, not in an entire region. Does not create a new phase, but it creates a higher dimensional defect by doing condensation. But if it satisfies our requirement, you can condense all the way to the codimension 1 and further condense it. That will produce new phase. Yeah. So this is a general theory. It gives you the criteria what kind of defect can be condensed. Condensed how many times? Yeah.
So then does it include case like you can condensing and then with some SPT phase?
This theory right now only for topological order, but for SPT phase, we expect the theory should be similar, but we haven't discussed on that yet. Yeah. That condensation, well, some part of can be said because the categorical description of SPT phase and SE phase is also known. So part of the condensation of topological order automatically imply certain condensation theory of SPT SET. But I don't know how complete it is. We could probably answer that question maybe later this year.
Okay, thank you.
U1 or even SU2.
Continuous symmetry so far is beyond our mathematical framework. But only thing I can tell you is that once you have a continuous symmetry, the category become infinite type. It's not finite type anymore. So, but we believe that. So what we show in this picture is that the condensation theory is really a condensation of higher algebra and higher representation theory. But that aspect have nothing to do with finiteness. You can work with the category with infinite types. For example, a lot of this structure already appeared in the irrational conformal field theory. In the irrational conformal field theory, you don't get the modular tensor category anymore, but you don't get a modular fusion category anymore, but you get a non-semi-simple version of modular tensor category in which the duality, the fully dualizability is gone. You don't have that, but you have some weaker notion of duality. You can still work with that. And you can also, the conformal field theory also rely on the representation theory of certain E2 algebra. In that case, you still have a braided tensor category, which is again E2 algebra. You can consider algebra object in that category, which give you, which is something you can condense. At the same time, they are also characterized closed CFT. That's something similar. And in that aspect, we believe if you work with continued groups, that aspect should be remain the same. Thank you.
Okay, so since we are slightly over time, so let's just thank Professor Kong Liang again.
Thank you very much.